I'm Dr.B.Krishnaveni, working as an assistant professor in Department of Mathematics, Aditya University. So today we are discussing about an application of a partial derivative, which is nothing but maxima and minima of a function in two variables. So we all know that how to find out the maxima and minima of a function in one variable. There we use the derivatives. Now we are calculating for the function in two variables. Here we will use partial derivatives. That's what we call it as an application for partial derivative. So now let's see. That is what is our lecture outcome for today lecture is evaluating. Student will be able to evaluate maxima and minima of a function in two variables. So now let's see what is the working rule to find out maximum and minimum of a function in two variables. That is f of x comma y. First find out dou f by dou x and dou f by dou y and equate them to 0. That is dou f by dou x is equal to 0, dou f by dou y is equal to 0. Solve these equations for x and y. Then we will get a pair of values like a1, b1, a2, b2, so on. That is the first step. Next we will find out L, M and N values for each pair of values. Here what L is equal to dou square f by dou x square. M is equal to dou square f by dou x dou y. N is equal to dou square f by dou y square. And let's find for each pair of values. Then we will move to the step 3. What's the third step is, we'll calculate ln minus m square and we'll see with that at what point it is having maximum value and minimum value or no max or minimum, etc. Suppose if the value ln minus m square greater than 0 and less than 0 at a point a1 comma b1, then we say that the point a1 b1 is the point at which the function has maximum, and f of a1 comma b1 gives the maximum value. Now if ln minus m square greater than 0 and l greater than 0 at the point a1 b1, then we call a1 b1 point is the point at which the function has a minimum value, and f of a1 comma b1 gives the minimum value of the function. Now still we have cases, what that is, if ln minus m square is less than 0. So if you see the first two cases, we are dealing with ln minus m square greater than 0, for which L less than 0, L greater than 0. So there is a case that we will get ln minus m square less than 0 as well is equal to 0 also. Let's see the third case, that is whenever ln minus m square less than 0 at a point a1 b1, then f of a1 b1 is not an extreme value, that is it has neither maximum nor minimum at a point a1 comma b1. And what extreme value, we know that extreme value is nothing but it's a maximum or a minimum of a function. So hence in this case we call that point a1 b1 is a saddle point. So next we will see the last case, whenever ln minus m square is 0 means at a point a1 b1, then there no conclusion can be drawn about maximum and maximum or minimum, and it needs further investigation. That means whenever ln minus m square is equal to 0, we are not able to get the conclusion by using this, hence that needs further investigation. Similarly, we will examine the same for other pair of values a2, b2, a3, b3, so on. So from this we will get what is the maximum and minimum value of a function in two variables. So here we will know we need to get the notation about what is L, M, N, and from that we need to draw the conclusions. Similarly, the same notation can also be replaced with R, S, T also. That is dou square f by dou x square, S is dou square f by dou x y, and T is dou square f by dou y square. Let us discuss the first question in this. Find the maximum and minimum values of x cube plus 3xy square minus 15x square minus 15y square plus 72x. So, given fxy, that is x cube plus 3xy square minus 15x square minus 15y square plus 72x. Differentiate above with respect to x, that is dou f by dou x. With respect to x, we are doing is y constant, x cube derivative 3x square, 3 into 1 into y square plus 15 into 2x, constant minus 0, 72 into 1, which is 3x square plus 3y square minus 30x plus 72. Now differentiate with respect to y. Here x constant, x cube derivative 0, 3x, y square derivative 2y, minus 15x square constant is 0, minus 15 into y square derivative 2y, plus 72x again constant is 0, derivative is 0. Therefore, what this will be equal to? 3x into 2x is 6xy, minus 15 into 2, 30y. Let it be equation number 3. So, here equation 1 is the given equation, dou f by dou y is 2, x is 2, dou f by dou y is equation number 3. Now, next need to find out L, M and N. What L is equal to? Dou square f by dou x square. That is dou by dou x of dou f by dou x. What dou f by dou x is? 3x square plus 3y square minus 30x plus 72. Do with respect to x partial derivative, which is equal to 6x plus 3y square derivative 0 minus 30 into 1 plus 0. So, which gives 6x minus 30. Next, differentiating 3 with respect to x, which is m, dou square f by dou x dou y. That is dou by dou x of dou f by dou y. Dou f by dou y is 6xy minus 30y. Now, derivative with respect to x partially, 6 into 1 into y minus with respect to x 30y constant, derivative 0, which is 6y. Next, differentiate 3, that is dou f by dou y with respect to y again, which is n, dou square f by dou y square. Dou by dou y of dou f by dou y is 6xy minus 30y. That is equal to 6x into y derivative is 1 minus 30 into y derivative is 1, which gives 6x minus 30. Now, to find out the critical points, we need to equate dou f by dou x and dou f by dou y to 0. That is dou f by dou x is equal to 0, dou f by dou y is equal to 0. If dou f by dou x is equal to 0 means you got the equation 3x square plus 3y square minus 30x plus 72 is equal to 0. Let it be equation number 4. And dou f by dou y is equal to 0 implies 6xy minus 30y is equal to 0. And from this, you can have 6 into x minus y into 0. That means you are getting two cases, either x minus 5 is equal to 0 or y is equal to 0, which means x is equal to 5 or y is equal to 0. Now, substitute x is equal to 5 in equation number 4. If you substitute x 5 in equation number 4, 3 into 5 square plus 3 into y square minus 30 into 5 plus 72. Simplification, 3y square minus 3 is equal to 0. Further simplification, we got y square is equal to 1. Therefore, what y is equal to? Plus or minus 1. So, hence at x5, we got y is equal to minus 1 and plus 1. Now, substitute y is 0 again in equation number 4. Then that equation becomes 3x square plus 0 minus 30x plus 72 is equal to 0. From this, we got the equation as x square minus 10x plus 24 is equal to 0. What are the factors for this? X minus 4 into x minus 6 is equal to 0. So, therefore, x is equal to 4, x is equal to 6. So, hence at y is equal to 0, we got 2x, that is x4, x6. Hence, what are the critical points here? For x is equal to 5, we got y is equal to plus 1 minus 1. And for y is 0, we got x is equal to 4 and 6. Therefore, the critical points are 4, 0, 6, 0, 5, 1, 5, comma, minus. Now, at each point need to find out the conditions. For that, we need ln minus m square value. Now let us take at the first point 4 comma 0, find out L value. L value, what is L is? We got L is equal to 6x minus 30, substitute the point. 6 into x is a 4 minus 30 it is, which is minus 6, which is less than 0. Next find out M value at 4 comma 0. What M is equal to? 6y. So 6 into y is a 0, that is a 0. And n is equal to, now again what n is? 6x minus 30. Therefore we got again is equal to minus 6. Now find out ln minus m square. L is minus 6, n is minus 6, minus m square, 0 square, which is equal to 36 greater than 0. Now the condition we got ln minus m square is greater than 0. And what L is? Less than 0. If ln minus m square greater than 0 and L less than 0 means, obviously what we will get? The point having, the function having the maximum value at that point. Therefore, A is the point of maximum for f and the maximum value is given by f of 4 comma 0. Substitute the point in the given function. You got the value is equal to 112, which is the maximum value of the given function. Now find out the same at the second point at 6 comma 0. L value 6 into x minus 30, 6 which is greater than 0. M 2 into y, 2 into 0 is 2, 0. N is equal to 6xy minus 30, that is again 36 minus 30, which is equal to 6. Find out ln minus m square. 6 into 6 minus 0 square, 36 again greater than 0. Now what L value here is? 6, which is greater than. Now what condition you are getting at this point? Lm minus m square greater than 0 and L greater than 0, which means f has minimum at that point. So what point here it is? 6 is 0. So therefore B is the point for which f has minimum and the minimum value is given by f of 6 comma 0. Now substitute x is 6 and y 0 in the given function. Then we got the answer is 108, which gives the minimum value for the given function. So now let's verify for the remaining 2 points. At a C 5 comma 1, find L value 6x minus 30, that is 6 into 5 minus 30, 0. M is equal to 2y, 2 into 1, which is a 2. N is equal to 6x minus 30, 6 into 5 minus 30, again 0. What ln minus m square values? L into n, that is 0, 0, 0, minus m square, 2 square, which is minus. So that means we are getting ln minus m square less than 0. Now do same for at the point 5 comma minus 1. L 6 into 5 minus 30 by taking x is equal to 5. M is equal to 2 into minus 1, that is by taking y is equal to minus 1, which is minus 2. N is equal to 6 into 5 minus 30, which is equal to 0. Now what again ln minus m square for this point is equal to 0 minus, which means L0, N0, 0 into 0, 0 minus m square. What m value you got? Minus 2, that is minus 2 whole square, minus of 4, that is less than 0. So that means in these two cases, that means at these 2 points at C and D, we are getting the condition as lm minus m square less than 0. So whenever we are getting this means we say that at that points the function has neither maximum or minimum. So whenever ln minus m square less than 0 at a point, we call that point is the point at which the function has neither maximum or not minimum. So that means, nor minimum, that means it has no maximum or minimum at that point and we call that points are saddle points. Hence at a CD, that is 5 comma 1 and 5 comma minus 1, we are getting the condition like ln minus m square less than 0 for which the function has neither maximum nor minimum. Therefore, we call this point C, D are saddle points. For the remaining 2 points, that is A and B, we are getting at A we are getting maximum value, at B we are getting minimum value for the function, hence we call those points are extreme points. Extreme points are nothing but the function at the point at which the function has maximum or minimum values. So now next is Lagrange's method of undetermined multipliers. What this method is? It is also a method by which we can find out the maximum of a function or minimum of a function. Lagrange's method of undetermined multipliers. Let us consider f of xyz be a function of three independent variables xyz, where x, y, z are connected by the relation phi of x, y, z is equal to 0. Now, let us discuss about the working rule of this method by which we can find out the extremum of the given function. Suppose it is required to find out extremum of the function f of xyz subject to the condition phi of xyz is equal to 0, which means we need a function, we need a maximum or minimum value of the function f of xyz which is subject to the condition phi of xyz is equal to 0. Let it be 1. Now, let us start with the step 1, that is we need to form Lagrangian function given by f of xyz, that is capital F of xyz is equal to small f of xyz plus lambda phi of xyz. Here lambda is called Lagrangian multiplier, which is determined by the following conditions. Now step 2. Obtain the equation dou f by dou x is equal to 0. So what f is? F plus lambda phi. So with respect to x means dou f by dou x plus lambda into dou phi by dou y equate to 0. Next, dou f by dou y is equal to 0, that is dou f by dou y plus lambda dou phi by dou y is equal to 0. And dou f by dou z is 0, which is dou f by dou z plus lambda into dou phi by dou z is equal to 0. Let the equations represented be with equation number 2, equation number 3, equation number 4. Now need to solve all these 4 equations, that is equation number 1, 2, 3, 4. Then we will get the values of x, y, z. So obtained will give the stationary point of x, y, z, at the point for which the function has a maximum or minimum. So let us have the clear idea about the method by discussing this question. Find the dimensions of a rectangular parallelepiped box open at the top of maximum capacity whose surface area is 108 square inches. So now need the values of x, y, z square, that means the dimensions of the rectangular box which is parallelepiped box such that it is opened at the top so that it is having a maximum capacity. Now let us take x, y, z be the length, breadth and height of the box which gives the dimensions, and let V be the volume and S its surface area. And we all know that volume is equal to x, y, z, that is length into breadth into height, it is equation number 1. And now given what surface areas, and if you take any rectangular box for example, we will get 2 surfaces, that is 2 times of xy surface, 2 surfaces regarding yz and 2 with respect to zx. That is what the surface area is given by 2xy plus 2yz plus 2zx. But here we will take the surface area as xy plus 2yz plus 2zx. Y means here the box, that is rectangular parallelepiped box, is opened at the top. That means one surface is not there, which is empty. So that is what not it is only 1xy plus remaining surfaces will have, that is what 2yz plus 2zx. That means if you take the perfect rectangular parallelepiped box, it will contain 6 surfaces. But here we have only 5 because the box is opened at the top. So that is what The surface area is given by xy plus 2yz plus 2zx and is given as 108. Let it be equation number 3. So hence we can write the equation as xy plus 2yz plus 2zx minus 108 is equal to 0. Now what is phi of xyz is the condition. So that's why we will take it as xy plus 2yz plus 2zx minus 108, because they are asking the dimensions of the rectangular blocks for which the surface area is 108 square inches. Means the surface area becomes the condition. So that's what we represent that with phi of xy. Now we need the dimensions for which it is having maximum capacity. So hence the volume should be maximum. Hence we have to take we have to maximize one, that is volume, subject to the condition 2, that is surface area. Now find out the Lagrange's equation, that is our Lagrange's method. The first step is need to form the Lagrange's function. Capital F of xyz is equal to, and here we will take the function v as v of xyz plus lambda condition of phi of xyz. So now what capital F is equal to? Xyz plus lambda into xy plus 2yz plus 2z plus 2zx minus 108, that is 108. Next find out dou f by dou x and dou f by dou y. What dou f by dou x is? With respect to x, that means y constant, z constant here, and we need to equate to 0, and that becomes with respect to x 1 into yz plus lambda into 1 y constant is 0, 2z into 1 constant 0. You got the equation as yz plus lambda into y plus 2z is equal to 0. Simplify up to you are getting in this way. You got minus lambda is equal to yz by y plus 2z. Let it be equation number 3. Next find dou f by dou y. The equation equate to 0. On doing the derivative with respect to y, you got xz plus lambda into x plus 2z is equal to 0. Simplify and you got minus lambda is equal to x by x plus 2z. Let it be equation number 4. Similarly, find out dou f by dou z equated to 0. On finding this, we got minus lambda is equal to x by 2y plus 2x. And if you see equation number 3, 4, 5, you are getting RHS are same, that is minus lambda, minus lambda, minus lambda. So hence you can equate the LHS, or else from 3 and combine the equations 3 and 4. Since both RHS are same, you can equate the LHS. And from this you got y into x plus 2z is equal to x into y plus 2z, which implies xy plus 2yz is equal to xy plus 2xz, which implies 2yz is equal to 2xz. Finally, got an equation y is equal to x, that is the relation. Now, from equation 4 and 5, since again RHS are same, let us equate the LHS, that is xz by x plus 2z is equal to xy by 2y plus 2x, which gives z into 2y plus 2x is equal to y into x plus 2z, which implies 2yz plus 2xz is equal to xy plus 2yz, which implies 2xz is equal to xy. From this xx cancel, you got that implies 2z is equal to y. Therefore, you got the relation between z and y, that is 2z is equal to y. Let it be equation number 7. Now combine 3 and 5. So if you combine 3 and 5 and if you are equating the LHS, you got the relation 2z is equal to x. So hence from equations 6, 7 and 8, what we can draw finally is x is equal to y and y is equal to 2z. So from this you got x by 2 is equal to y by 2 is equal to z. Now substitute this in the given condition, that is in the surface area. xy, what x is? Y is x, so x into x plus 2x into z, that is x by 2 plus 2yz 2x by 2x is equal to 108. Simplify, you are getting 3x square is equal to 108, that is 108, x square is equal to 36, therefore x is equal to 6. By using x is equal to 6 and by this relation, what y is equal to? Again 6, z is equal to 3 it is. Therefore, the dimensions of the box are x is equal to 6, y is equal to 6 and z is equal to 3, for which it is having maximum capacity, that is volume. So, now let us have the another question in the same method. Find the point on the plane x plus 2y plus 3z is equal to 4 that is closest to the origin. So, closest means nearer to the origin. So, hence from the plane to the origin, we need to find out the nearest means we need to find out minimum distance. So, first let us take P, X, Y, Z be the point on the given plane. And we all know that OP is equal to root of x square, that is distance between the origin to the point, given by root of x square plus y square plus z square, which can be written as OP square, that is equal to x square plus y square plus z, which is giving the distance. So, need to find out the point at which it is closest to the origin, point on the plane which is closest to the origin. So, which we are getting the distance OP squared, or we can write it as OP square. We need to find the minimum for this function. So, that is what let us represent this with f of x, y, z. And that point must be on this plane, that is the condition it is. So, that is what we are represented the plane with the condition, that is phi of x, y, z is equal to x plus 2y plus 3z minus 4. Equation number 1, equation number 2. Now, we need the point should be closest to the origin, means it should be minimum. That is what we have to minimize 1 subject to the condition 2. Now, by Lagrange's method, write f of x, y, z, that is capital F of x, y, z is equal to small f of x, y, z plus lambda phi of x, y, z. F of x, y, z is equal to small f is x square plus y square plus z square plus lambda into phi is x plus 2y plus 3z minus 4. Now, find out this 3 equation. First, dou f by dou x is equal to 0 with respect to x. 2x plus 0 plus lambda into 1, remaining all are zeros, is equal to 0. From this, you got 2x is equal to minus lambda. Next, dou f by dou y is equal to 0. 0 plus 2y plus 0 plus lambda, all zeros except this. And from this, you got again y is equal to minus lambda, and by taking dou f by dou z is equal to 0, now f with respect to z, 0, 0, 2z plus lambda into 0, 0, 3 into 1, that is 3, 0, which gives 2z plus 3 lambda is equal to 0, 2 by 3z is equal to minus lambda. Let us represent these 3 with equation number 3, equation number 4 and equation number 5. Let us combine from 3 and 4, minus lambda is equal to 2x, minus lambda is equal to y. So, hence equate the LHS, that is 2x is equal to y. Equation number 6 it is. Now, from equation 4 and 5, what is 4 and 5 are? Y is equal to minus lambda, 2 by 3 is equal to minus lambda. So, therefore, you got the relation as y is equal to 2 by 3z, equation number 7. Finally, from equation number 3 and 5, 2x is equal to minus lambda, 2 by 3z is equal to minus lambda. From this, you got 2 to cancel, z is equal to 3x. Let it be equation number 8. From 6, 7, 8, you got 2x is equal to y and y is equal to 2 by 3z, which gives y is equal to 2x and z is equal to 3x. So, now substitute y 2x and z 3x in the given condition, that is x plus 2 into 2x plus 3 into 3x is equal to 4, which is 14x is equal to 4, that is x is equal to 2 by 7. So, now what y is? 2 into x, it is 2 into 2 by 7, 4 by 7. What z is? 3x, it is 3 into 2 by 7, which is 6 by 7. Hence, we got the point on the plane which is nearest to the origin, that is 2 by 7, 4 by 7, x, y, z, those are, that is 2 by 7, 4 by 7 and 6 by 7. So, this is the Lagrange's method by which we can find out the maxima or minima of a function. Hence, In this lecture, what we discussed is about finding maxima and minima of a function in two variables. So not only by using the general method, we went through the method called Lagrange's method of undetermined multipliers. So hence, from this lecture, you come to know how to find out the maxima and minima of a function in two variables. Thank you.